Hello and welcome to another presentation in the LADAL Opening Webinar Series 2021. My name is Martin Schweinberger, and together with Michael Hoare, I'm co-directing LADAL, the Language Technology and Data Analysis Laboratory at the School of Languages and Cultures at the University of Queensland. Before we continue, I would like to say that we as members of the University of Queensland acknowledge the traditional owners and their custodianships of the lands on which we meet, and we pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. I'd also like to say that we acknowledge and recognize their valuable contributions to Australian and global society. If you'd like to know more about LADAL, you can find LADAL via our URL on the homepage. You can also find more information about the upcoming and past talks in the LADAL webinar series on the events page. You can follow us on Twitter so that you're informed about upcoming events and news, and you can also contact us directly via email. It's a real pleasure to introduce today's speaker, Mikko Laitinen. Mikko is Professor of English Language at the University of Eastern Finland. He has been a member of the Academy of the Finland Center of Excellence and Research Unit for Variation, Context and Change Varying since 2000. He previously worked as Professor of English at Linnaeus University, where he's one of the two founding members of the Center of Data Intensive Sciences and Applications, DISA, a multidisciplinary big data research consortium that consists of scholars in the humanities, computer science, computer scientists, mathematicians, and social scientists. His research focuses on the role social networks play in language variation and change, computational, sociolinguistics, and digital humanities. It's a real pleasure, and I'd like to hand over to Mikko.
Thank you, Martin, for this kind words. Let me share my screen. You should be able to see my PowerPoint, I would imagine. Is that so?
Yeah.
Yes.
Perfect.
Yeah. Thank you for the organizers for inviting me. It's a great pleasure. It's really LADAL offers a very interesting platform for us in social sciences and humanities and linguistics in particular, for getting to for increasing interdisciplinary collaboration and increasing data intensiveness in our research. So this is really a wonderful platform that you guys have developed, and I'm happy to talk about my ongoing research that focuses on societal big data. By the way, during the presentation or after the talk when it's made available, if you have questions, my email is on the screen, so please feel free to be in touch with me. Let me just do one small thing on my watch so I can time. What I'll talk about here is actually based on collaborative work on many fronts. On the one hand, work carried out of my own group in the English section where we have sociolinguists in the group. And the second layer of the work is provided by an up-and-coming sort of emerging research infrastructure or digital research infrastructure in the Finnish context called Finclaria, which is a common language research and technology infrastructure. And one part of this is actually funded by our sort of internal bridge funding related to Finclaria, and is one part of Finclaria, which consists of all the Finnish universities, or nearly all the Finnish universities, where there's humanities research humanities faculties in university. And then one big part, one big contributor to this research is the Center for Data Intensive Sciences and Applications. These are in southern Sweden, where I used to work. And as Martin said in his kind introduction, it's a sort of an interdisciplinary consortium of about 40 to 50 experts from different fields, from computer sciences, information visualization, mathematics, statistics, social sciences and humanities, and really aiming at fostering data-intensive research in the university level, and generously funded until the end of this year. We have had a wonderful funding for 5 years. And for instance, the computer scientist who's included in the work that I'm talking about today is being funded by these. My talk combines social linguistics and computer science. It's actually based on a recent paper. So basically, everything that I talk about when it comes to methodology, you can find more details of the methodology in the paper. It's a paper, a recent special issue on computational social linguistics, where we talk about digital social networks and language change. A joint paper together with myself and Masud Pateli and Jonas Lundberg.
Mikko, may I interrupt really quick? I'm not sure, could the audience let me know? I'm having some audio difficulties, because sometimes you're very loud and sometimes you're very, I can't hear you very well.
Okay, I'll try to be a bit closer to.
That's much better.
To the microphone, okay.
Thank you very much.
Yeah. And our research in the article in the talk focuses on societal big data. Well, that is to say, data harvested from social media applications, Reddit, Facebook, and Twitter. And as we all know, these platforms of digital applications offer us an access to both structured and unstructured data and metadata. And it's not a very sort of a big insight, in the sense that these applications offer us a large source of language data in naturalistic settings, and plus they offer us a relatively easy access to of data from a very large number of people. And hence, as we all know, societal big data is increasingly being used as material in SSH areas. So whether that be linguistics or cultural studies or something else. This has led to the emergence of new fields in linguistics. One example of this is, for instance, computational social linguistics. For instance, the special issue which I mentioned, edited by Jack Reeve and his colleagues, is one big achievement in this new field. Computational social linguistics does what the name says. It intersects social linguistics with computational techniques, and researchers in this field analyze large and often very complex data sets, some of which have been harvested from social media. And of course, the objective of the field is to get a better insight and better understanding of language variation and change and its social embedding. And societal big data, as we all know, then offers a wonderful test bed or testing ground for for various old questions within this field. So how do languages change, and what happens in language change, and how is it conditioned by the social structures in which it is used? And of course, societal big data offers us a very large data for this endeavor. So far so good, and rather simple issues, so to speak. But there's one serious concern and problem related to societal big data, that it's not very rich. We have very limited access to social background information in societal big data. There's no information of account holders, occupation, social layer, gender, and things like that. This is also seen in the articles in the recent resolution in computational sociolinguistics. There are, I believe, so far altogether some 40 articles, and out of these 40 articles, 6 or 7 use societal big data. The extra-linguistic background information that is used in these 6 articles is or contains the following. A few of them use geolocation properties. One of them uses timestamps associated with each account. One uses manually extracted information. So there's really sort of a serious lack of background information related to societal big data. And there are, of course, various reasons for that. Is that the most significant of these is that this type of information is worth money. So proprietary reasons we don't get, or academic research is, or the data sets that we get rather easily do not have this information for proprietary reasons. When it's shared, or when such information is shared, it is often self-reported. So that is to say, let's say that the users' names, for instance, are self-reported data, but as we all know, we can appear under any name in the digital domain. So there are some serious concerns of reliability. In addition, I think we're still hampered by relatively recent and totally unethical practices of linking harvested data with background data. And I'm here referring to, for instance, the Cambridge Analytica scandal a few years ago or 2 years ago. So there are serious ethical concerns of linking language data with social background information. And this has serious implications for sociolinguistics. As I've said, the focus so far has primarily been on sort of the computational text analysis and on areal variation mostly. And I would say, as a sociolinguist by training, or somebody who's been working with language change for 2 decades or more than 2 decades, I would say that there's actually less focus so far has been in computational sociolinguistics on language change and the processes related to language change. The consensus view in sociolinguistics is that language change must, or it consists of 2 processes. The birth of new forms, the actuation, and then their spread, or the spread of new forms into communities, their diffusion. according to a widely held view, actuation is functional. So it involves remappings of forms and functions. But diffusion, on the other hand, is a social phenomenon. It requires a connection between speakers and then the broader societal structures within which speakers belong. And when we have no access or limited access to rich sociolinguistic background information, I would argue that the scope of computational sociolinguistics, despite the promising, very promising, various promising aspects of the field, is the scope of the field so far has been rather limited. And also the big social media data has remained only of partial use. So basically, most of the studies have focused on where background information has been used, extralinguistic background information has been used in these studies, as the focus has been on actuation, how and where, and typically where, because we have access to the geolocation properties, has been. So where, how, what and where questions have been focused. So what kinds of new forms have emerged, whether they be lexis or grammar, and where, that is to say, from which particular locations they have emerged. But we don't really actually know anything about the diffusion, the spread of these forms of new items into communities. So my aim here is to find solutions on how to enrich big data, also societal big data, with richer information, with rich social information. I'm going to use, or our method uses interaction data available on Twitter. So interaction data like frequency of communication, friend and follower patterns, retweets, and things. I'll go into details in a moment. We argue that they can be rather easily quantified. They're first of all freely available. They can be quantified and they can be used as proxies for social parameters. There are a number of benefits. They're participant-centered, so they do not depend on us or an external analyst creating categories, saying that we want to create social layers and decide that we go for three-level social layer division based on either our intuitions or external information that we have at our disposal. Interaction data is participant-centered. We can only, we as researchers can only observe. They're also automatically generated, meaning that we can only observe, we can actually observe authentic behavior. It's not really possible. I mean, it's possible to tamper with these, but it would sort of be seriously, we can say that the size of the data that we can access actually, masks or hides an individual account who might sort of tamper with these data. They're relatively, reliable. The downside of this is that the downside to this is that the interaction data it takes some time to extract them, and constructing the categories also requires some degree of computational competence. But again, I think that this can be rather easily accomplished or overcome through interdisciplinary partnerships. So we can involve best experts in each task that work. But overall, I would say that they sort of this is a rather nice topic for digital humanities or data-intensive humanities research. because it requires experts from different fields. When we use interaction data, we rely on social network theory as our theoretical framework. I'm just going to very briefly go through social network theory. I know that you're interested in this are most likely familiar with this, but just want to present a brief overview, because it actually what we do in terms of methodology development is actually closely connected with the research endeavors in deepening the understanding of social network theory using societal big data. But as we all know, the social network theory stems from the idea that we as individuals form personal communities that are meaningful frameworks in our daily life. And a network is the sum of the relationships that we contract with others in our life. They can be quantified. That our ties or the relationships can vary on the scale of from X to Y, between 0 and 1 or -1 and 1 and so on. And on the one end, we have strong and multiplex ties. So if the sum of the relationships that we contract with the others form a dense network, it means that individuals are linked through close ties, such as family and friends, for instance. Or at the one end of the scale is weak ties or loose networks if and when individuals are predominantly linked through occasional and insignificant ties, like more or less acquaintances. Or it can be anything in between. When it comes to language variation and change, there's ample evidence that networks contribute to language maintenance and change. The Milroys, for instance, starting from the 1970s, have done pioneering work on this, and the network model has been applied to the study of language variation and change in a range of contexts. And the consensus view is that the loose-knit networks tend to promote the spread of new linguistic forms, so that the loose-knit networks play a role in the diffusion of forms that have emerged. And on the other hand, strong and multiplex networks tend to lead to communities that resist change. The reason for this, for the weakness of strong ties, that is to say, strong ties leading to language maintenance, it's been argued that there's clearly a societal, social reason for this, is that if and when we live in strong tie communities, there's a sort of an inherent fear of losing one's social standing if we bring innovations into this type of community, based on well-known idea by well-known publications by Mark Granovic, starting from the early 70s, who argues that adopting new ideas in this type of a strong, close-knit setting is socially risky. And since we are social animals, we kind of don't want to rock the boat in dense social structures. So basically, evolution has told us that we don't want to risk our social standing if we live in a close-knit group. And this is actually an old question, has been tested widely tested in sociolinguistics throughout the 70s and 80s and 90s, and both in contemporary societies and historical settings as well. The problem with this is that from our research purposes is that it's primarily based on very small ethnographic. It's been suggested that the ethnographic methods that are used, for instance, by the Middle West themselves, that they limit the size of networks that can be studied using the methodology to a few dozen individuals. They say something that they say estimate that it's roughly the upper limit of a network size that can be accessed is around 30 to 50. And ethnographic methods also are problematic for tracing networks of very mobile informants. So it's basically good for tracing non-mobile informants or networks of non-mobile informants. So, as I said, the maximum size of traditional methodology is around 30 to 50 individuals. However, if we look at data from average network sizes, at least in the Western society, there's ample evidence from social anthropology that we maintain networks that are at least 3 to 5 times larger than the upper limit of the ethnographic model. McCarthy et al. 2001 estimate that the average network size, at least in North America, is around 290 nodes. And there's estimates that vary, to some extent, but all of these tend to point out that it's actually around at least over 100 nodes that's the lowest estimate of the average network size. My colleague Jonas Lundberg and I we did a study on online social networks in the Nordic region, and our estimate is that a median size of an average network is around between 200 and 330 nodes. And we used a sort of a rather nice machine learning experiment that enabled us to zoom into what we call genuine human accounts. So basically we excluded celebrities and things like that, and verified accounts and things, and just harvested a lot of information and did a bit of pruning and came up with this median. One might also question is that, well, since societal big data looks into online communities, is that they might be different from traditional sort of offline face-to-face communities, but there's actually increasing evidence that the structural characteristics of online communities and offline communities are actually rather minimal. Dunbar et al. Robin Dunbar and his colleagues published a study on this earlier this year. So basically what I have is a dual objective. I want to test an old question with big data, an old question in social linguistics. What happens to what extent is the characteristics of social networks constrain language change? And at the same time, what we want to do is to provide ways of making big data richer by adding social information. And social information in this case is interaction. Now let's take a look at this, the interaction data and the model we have developed. So basically on Twitter, what we're doing is what we're dealing with is a graph-based network that centers around an ego. So that's to use the terminology in social networks, is the anchor in the network. And luckily for us researchers, is that Twitter data what we have is that all the egos are identifiable with a unique identifier, an ID, as those of you who work with Twitter data. Then we have the nodes in the network. So accounts that are somehow connected with the ego. And of course, all of these nodes are also have a unique identifier. And then edges in this model consist of interaction. So for instance, this is a simplification when we have a network of 6 nodes, or 5 nodes centered around an ego in the middle. And all the interaction in this graph-based network can be traced. So what we have in this particular example is that the blue lines in the network indicate follower patterns. So a node following another node. So in this case, the ego follows nodes A and E, but A and E do not follow the ego. So there's a sort of a one-way link. And then the black lines or the black arrows indicate two-way relationships with friend and follower node. So ego follows D, and D follows the ego, and hence the black one. And it also shows that the nodes in the network do not necessarily have to go through the ego, but they can follow each other across the network, like in the case of A and B following each other. So what we did for this experiment, we took 35 randomly selected accounts from various urban centers in Britain. They were selected only based on 2 criteria. That the primary location of the egos needed to be in any of these 5 urban centers of Belfast, Birmingham, Bristol, London, and Manchester. And the network sizes of the egos had to be over 30, stemming from the idea that we wanted to test, first of all, of how easy or how difficult it is to collect data. We had collected similar data from the Nordic region already, so we kind of knew that. But we also wanted to test the computer time required to establish the network values. The Twitter API enabled us to collect 3,200 of the most recent posts of all the accounts, of each one of the accounts in the network. So each one of the accounts connected to the ego. And it also enables us to download the interaction data. That, of course, that excludes if an account is private, then that results in a 0. The loss ratio for private accounts range varied heavy, but overall, I think we got I'm going to show the overall size of the data. resulted in a rather nice data set that enables us now to label the 35 randomly selected accounts, give a value of social, of a social standing of the ego. What we did in terms of methodology is that we started setting up some form of value. We call it the alpha value for each ego node, based on how often the nodes in the network communicate with each other, how dense the network is, what's the distance between all the nodes in the network, how well the nodes are connected to each other, and I'm going to go into details of these in a moment, and of how similar the nodes are. So basically, trying to come up with ways that we could measure the social standing of each ego. And as I said, the alpha values here are used as proxies for social parameters. They somehow index something of the social standing of the ego. The method is multidimensional. As you can see, it uses 5 different characteristics, of which one of them is frequency. Frequency is usually the key. Frequency of communication is usually the key in ethnographic methods. But the objective here is that we wanted to look beyond frequency, which is now the house. It's sort of increasingly sort of a household method in the study of social networks outside linguistics, outside sociolinguistics. That is to say that networks are multidimensional, that they consist of a range of, that the basis the basis used to establish network values is multidimensional. Just going to go through the 5 different algorithms that we used. First of all, we established edge weights, so that look into the frequency of communication. So basically, we encoded interactions based on the frequencies in the network. This is an example network of around 30 nodes around the ego, which shows the edges and the nodes with no edge weights in the model. What we did, we used a simple algorithm that gives a different way to interaction parameters, and also accounts for the age of the account and the total number of interaction in the network. We use the model. We can see that the graph changes quite. On the one hand, we have the nodes, or the size of the individual nodes changes quite dramatically, depending on how significant these nodes are in the network. And also the line thickness, which shows the interaction patterns, changes quite dramatically. So some of these connections clearly interact with each other more often than some others. So the thicker the line, the more interaction there is. And we calculate the mean values of the edge weights for each network. We assume that if the network is strong, or strong pi network, the mean value is higher than that of the weak pi network. So basically, there's more communication. Individuals in a strong pi network are expected to have more interaction and more communication and more activities with each other than those in the weaker pi network. But that's used as one parameter. Then we did the network density, where we used betweenness centrality. That measures the extent to which people are connected to each other. And basically a ratio with which an account establishes the shortest path between any pair in the network. And the algorithm is here. And it results in two betweenness centrality values. On the one hand, we look at value spread. So we took the lowest value in the network and the highest, and then see what is the spread between the BCs for each node. So basically, how close to each other the nodes are. If the spread is low, that means that the nodes are more connected to each other, and the network consists of stronger ties, and vice versa. If the spread is large, then the nodes are not connected to each other, or are less connected to each other. Let's put it that way. And then we also look at the mean values for BC, for betweenness centrality, for this betweenness centrality measure. Let me show you an example. This is again, two networks. These are not from the data set. We can see that clearly see that the network on the left is looser than the network. There are some pockets within the weak tie network on the left, but overall, as a whole, the network consists of weaker ties than the network on the right. The BC spread for the weak tie network is around 0.55, and the spread on the right is 0.3. Now that kind of gives us an indication that we can visually confirm that the method could actually be used, but as part of the methodology. Then we use distance between the nodes, and here we rely on closeness centrality, which does exactly this. It measures the distance between nodes, and it's the reciprocal of the sum of the distances from one node to all the other nodes in the network. And this is the algorithm that we use. We basically use normalized values, so we can the direction of our measurements is the same for all of these five algorithms. Twitter is a directed graph network, as I have shown, where we have one-way links and two-way links. And so there are basically two CC values for each node, one incoming and one output. And we assume that if the difference between these CC values is low, the majority of the connections in a network are two-way links, and the network consists of strong ties. And on the other hand, if it's a one-way link, it's, if people are just, following each other, but the other nodes are not following them back, it tends to consist of it increases the likelihood of the network being weak. Let me go back to the example network. So here the ones that we used with the betweenness centrality. So on the left hand side, we visually can say something that the network on the left consists of weaker ties, and as we can see, most of the links in the network here are blue links. They're one-way links. Black links here are sort of two-way links, so people following each other. And as we can see, the majority of the links here are blue, whereas if we look at the network on the right, the strong tie network, the majority, or there's simply more two-way links in this particular network. And actually, if we look at the network on the right, there's only one one node here, which is there's only one. I'm just trying to draw here. I seem not to be able to do it. There's only one link here, which is sort of the odd one out in the strong tie network, and it's the one on the topmost node in the network. Whereas if we look at the weaker tie network, there are actually a number of these odd ones out, so there's a number of nodes that only contain one link, and that's through the ego, or one link to the network, and that's through the ego. The fourth model, or the fourth algorithm, it looks exactly this: is that how well are these nodes connected to each other? And this is something that we were thinking originally, and we couldn't find anybody using this particular model, looking into the proportion of disjoint nodes in the network. So basically, if we remove the ego node and all the links that either come or reach out from this particular node, how well are the other nodes in the network connected to each other? So basically, the fourth algorithm here looks into the proportion of disjoint nodes. So those that are not connected to any of the other nodes in the network other than the ego. Again, we can use these two networks to illustrate the methodology. If we remove the yellow ego node from the left, we can see that the proportion of disjoint nodes in the weak tie network would be larger than in the strong tie network. So basically, if we remove the ego from the strong tie network on the right, there's only one node that's not connected to all the other nodes in the network, and that's the topmost node, which only has one link, actually one two-way link to the ego. And then lastly, we look into how similar the nodes are. And here we rely on a pioneering study by Leslie Milroy, who carried out the ethnographic work in Belfast and observed that men were localized primarily in the three networks, in the three neighborhoods that she looked into. So they basically had more close-knit ties than meaning that they spent more time with the people who were just like them. So they were more similar to, they had they lived in close networks. They were more similar than all the other men in their networks than those who lived in the weak tie networks, or those who had more weak tie networks. Here we rely on what is known as Jaccard similarity coefficient, which is a symmetric measure that calculates how similar the two sets are. So basically, we look into the, we have two sets A and B. Jaccard similarity coefficient measures the proportion of items that are shared both by A and B. So let's give an example. If we have two networks, one from John, who has 136 friends, and Anna has 210 friends, and 89 of them are common. So the Jaccard similarity coefficient is 89 divided by the total, which is roughly 0.26. So higher average Jaccard similarity coefficient indicates strong ties, and vice versa. Again, we can look into this, these example networks. These are real networks from the academic community, by the way. I can't remember who they are, who they were, but we have used them as examples. So basically, in the weak tie network, The Jaccard similarity coefficient is 0.12. So the slower similarity between the nodes again adds to our methodological toolbox. Whereas for the strong tie networks, the Jaccard similarity coefficient is 0.9. So clearly the method is able to detect something or to detect similarities and could be used as again one way of one basis for social categories in societal data. So what we did here, these are simple algorithms. Once they've been created, they're run. So basically we download all the data. That requires a bit of computing power. No supercomputer though, 2 to 6 hours per account, results in a rather large data set. But then we can come up with the social coefficient, a mean for each row. So basically these are the 35 urban accounts. And as we have 6 different parameters here. And the parameters are the ones that I've just talked about. The BC mean, the between the centrality mean, between the centrality spread, Jaccard similarity coefficient, closeness centrality, disjointness, and edge weight. And I just wanted to say this is that the ethnographic methods, and by the way, I have the highest respect for the work that's been done previously using ethnographic methods. It's just that we wanted to add a data-intensive angle to this. But the ethnographic methods primarily, if we use the terminology or the algorithms that we use here, rely on edge weight. And if we look at the edge weight, most of these accounts would actually be weak tie network. So the lower the value, lower the mean value, the weaker tie the network is. And we calculate the mean for each row. So now account 1 gets a label, 0.57. And somehow indexes how the social standing of in relation to all the other accounts in our data set. So basically, this is the total data that we have in this particular study, with all the 35 accounts in the first column, the alpha values, the network values for each account in the second column. They range from 0.23 to 0.93. There's quite a lot of spread. And of course, they can vary between 0 and 1. The network sizes are in the third column. And as we can see, well, the median is 125. The range between 33 and 233. And again, I just wanted to highlight this, that most of the networks in the ethnographic models have been, less than 30 or less than 50, I would say, nodes. So basically what we can now do is access rather large networks relatively easily. And these networks whose sizes are well above the traditional the sizes of the networks in the traditional model and closer to the average size of human networks in general. And this experiment gave us roughly 6 million messages. That's in the fourth column, number of messages. 67 million running nodes. The average length of a tweet is in our data set is around 11 tokens. So rather sizable material as well. And then we use the labels, gave a label based on the alpha values. And here we have to experiment a bit in the sense that we use the median value as the cutoff point, so 0.47. Anything whose alpha value is above that gets a label of a strong type, and anything below that gets a label of weak type. We can sort of somehow also visually analyze this, and I think this, now that we're talking about data-intensive sciences and interdisciplinary collaborations, this is a very important aspect in the sense that we can complement this mathematical model or computational sociolinguistic model now with the visual analysis. This is done by our colleague Konstantin Pusher, who is an information visualization specialist. And here I'm just going to show the data from 8 accounts in the data set on the previous page. So what we see on the left is 4 accounts with the lowest alpha value. So those are the weak type, clearly the weak type networks. And by the way, if you're wondering where they're from, 2 of them are from London, one of them is from Belfast, and one of them is from Birmingham. We can visually confirm that the algorithms are able to distinguish networks and networks of different values. So clearly the accounts on the left are weaker or looser than the accounts on the 4 accounts with the highest alpha value, so the strong tie accounts. The sizes of these data sets are roughly similar. There's actually a tad more accounts in the strong tie networks, but we wanted to emphasize that the network size here is, or the sample sizes are roughly even. The geographic location of these highest alpha networks of highest alpha values, they range from Belfast, Birmingham, London, and Manchester. But an interesting feature, if we look at how many bridges there are across these networks, when we zoom in into this, into the weak tie, the 4 weak tie networks, there's actually a surprising number of links across the networks, despite the fact that they are from different areas, different geographic locations in Britain. Across these weak tie networks, we can compare this to the strong tie networks, which are clearly sort of or the networks that got the high alpha. And there are actually only 4 different nodes that act as bridges across the 3 networks: the purple, the blue, and the green one. The orange network is actually sort of a more isolated. And now what we can, so basically this was I'm running out of time. The idea here was to show how we can now establish social information which could complement the studies based on social media. We want to propose that it actually fixes a major limitation related to social big data. It enables us to ask new types of questions in computational social linguistics. How do new forms spread? I didn't have time to talk about we used the 6 million or the data set of 6 million tweets to look into the ongoing grammatical change. We're actually doing this right now, but I didn't have time to talk about this because I think that this is sort of the methodological development that we're doing here. Is actually more important for the development of the field of computational social linguistics as such. It takes the computational linguistics with a focus on text closer to being truly computational social linguistics. It enables us to look into the social parameters. And as I said, the requires some degree of computing power, but nothing, and we've tested the model with 35 accounts. Nothing prevents us from testing it with 35,000 accounts or 350,000 accounts or whatever number that is. We want to argue that social network information could be useful. It's far from perfect. It doesn't still give us access to information or like education or gender and things like that. But in the absence of other types of information, I think it offers a promising area for future studies. And I wanted to, this is the last slide, I wanted to highlight this, is that this has been a collaborative effort, that we have had experts for each part, each task. I'm a social linguist, I'm not a coder. Coding is done by my doctoral student, Masoud Fatemi. And by the way, the code that's used for these 5 algorithms, it's freely available. Test it, it's a Python code. Feel free to test it with networks if you're interested in networks. And we'd be more than happy to hear feedback of how we could improve, whether something could be added, something could be removed from the algorithms and so on. And in visualization, we have benefited from our collaboration with Dr. Konstantin Puscher from Linnaeus in Sweden. So it's basically, I wanted to thank their contributions as well. If you have questions and comments, feel free to be in touch with me. Laitinen@uni.fi is my email.